In this video, we're going to take what we've learned about pendulums, any pendulums, and apply it and learn how to apply it to analyze and find the frequency of oscillation for any pendulum that we're given. So for pendulums, and we call them physical pendulums, meaning that we're not specifically just talking about a simple pendulum, which is a mass on a string. Instead, we're talking about a very general pendulum. It could be, the piece of paper oscillating. It could be the rod oscillating. We came up with this result where theta as a function of time was going to be equal to theta max cosine omega t plus phi. And then we had where omega came from analyzing this situation. So remember, first of all, that if you find omega, which is the angular frequency, so omega is what we call the angular frequency, and its units are going to be radians per second. The stuff from simple harmonic motion also applies to this model of a pendulum at small angles, right? So omega is our angular frequency, and that omega is going to be equal to 2 pi times f, where f is just equal to frequency, not angular frequency. And the units of f are hertz, so cycles per second. And so that would be how many cycles does your pendulum complete in 1 second. And then lastly, we have t, which is the period, and that's equal to 1 over the frequency. So that's just something to kind of keep in the background as you're trying to solve problems, because you might be asked for the frequency, you might be asked for the angular frequency, you might be asked for the period, and you have to be able to move between them. As long as you know one, you can calculate all of the others. All right, so we'll focus on how to calculate omega. So again, the key result for pendulums oscillating at small angles is that omega is equal to m times g times d over I. So for any pendulum, you want to just be able to apply this. So you need to know what everything is. So g is just equal to our good old magnitude of the acceleration due to gravity. Remember to always put in a positive number for g, as we have all semester. It is the magnitude of the acceleration due to gravity. M, very importantly, is the total mass of the pendulum. So if your pendulum is a rod with a point mass glued onto it, then M is going to be the total mass of the system. D is the distance from the center of mass of your pendulum to the pivot. Distance from the center of mass to the pivot. So you might need to calculate the location of the center of mass in order to figure out what D is. When you do that calculation, you might as well do it relative to the pivot. And then lastly, I is our total moment of inertia for the pendulum. So again, you would combine the moment of some of inertia of all the parts of your pendulum. And so knowing those definitions for each of those parts of the equation will allow you to calculate the angular frequency, and therefore you can calculate the regular frequency as well as the period. One thing I will note here is something called the simple pendulum is simply going to be a massless string with a point mass that is at the end. So this would be what we consider to be a simple pendulum, and then everything else is what we consider a physical pendulum. And it could be anything, literally anything. So that could be the rod that is oscillating back and forth. It could be a square, as I've sort of shown, that's going to oscillate back and forth. It could be a combination of all of these. It could be a rod with a square at the end, and that then oscillates back and forth. Really anything that is not a simple pendulum we qualify as the physical pendulum. This equation works for both. For the simple pendulum, you can still figure out what the mass of the system is. What's the moment of inertia of a point mass relative to your pivot point up here. Where is the location of the center of mass, etc. So that equation is very general, applies to both physical and simple pendulums. Let me know if you have any questions.